Hello everybody. In this session, I'll explain the numerical problems of the 5th semester paper 5 of Davangere University syllabus. Okay, the first problem, I'll discuss the problems on the chapter Electron. The first problem, the drop of oil density 920 kg per meter cube falls freely in air of viscosity 1.824 into 10 raised to minus 5 Newton second per meter square with uniform velocity of 8.58 into 10 raised to minus 4 meter per second. When a vertical electric field of 3.18 into 10 raised to 5 volt per meter is applied, the drop moves at various speeds which differ from each other by small multiples of 5.39 into 10 raised to minus 5 meter per second. Calculate the value of electronic charge. Okay, so this problem is based on the final expression what we obtained while deriving the expression for charge of an electron in a Millikan oil drop method. Okay, so first let us take the given values one after the other. The density is given as 920 kg per meter cube, and this is coefficient of viscosity, that is eta is given. Okay, list the eta here, and the uniform velocity means it's a terminal velocity is given here. So please write down the terminal velocity as the given value. Then the vertical electric field is given here 3.18 into 10 raised to 5 volt per meter. And the drop moves at various speeds which differ from each other by small multiples, means this must be V2 minus V1 minimum. Okay. So electron charge is to be calculated here. The formula for calculating electron charge is this. Substitute, all the values are given here. Substituting the values, okay, we'll get the answer as 1.62788 into 10 raised to minus 19 coulomb. Okay, so next problem. Okay, next problem. The problem is like this. A water drop of radius 10 raised to minus 6 meter is charged with 1 electron. Calculate the electric field required to keep it stationary. Okay, so first only the radius is given here. List out the given values. Given value is radius is given and electric field is to be determined. Now the condition given here is a water with 1 electron. Calculate the electric field required to keep it stationary. Stationary means, so in the experiment we are using electric field, and also the drop is descending in a downward direction due to gravitational field. So the force experienced by the drop due to electric field must be equal to force experienced by the drop due to gravitational field when both the fields are in equilibrium. So the equation can be written like this. Now this is to be determined. So cross multiply it, but the mass of the drop is not given directly. Instead they have given a radius of the drop here. So use a theoretical formula for mass. The water drop appears to be spherical in shape. So you have to take a volume. So mass, we are writing it as density is equal to mass per volume. That formula we are using here. So mass is equal to volume into density. We have to take into consideration. Okay. So substituting the values here. Density of water, as it is a water drop, the density of water can be written as 1000. Substitute all the values in the formula. We'll get the answer as 2.564 10 raised to 5 volt per meter. Okay. So the next problem is again of the similar type. A charged oil drop is suspended in a uniform magnetic field. Uniform field, sorry, not magnetic field. It's the field means electric field we are using in this experiment. So uniform field, so that it neither rises nor falls. Again the same condition here. That is force due to electric field must be equal to force due to gravitational field. If the mass of the drop is given in this formula, and asking, that is the charge is to be determined. Okay, so write down the given values first. Okay, list out the given values. Electric field is given, mass is given, and E is to be determined. So the condition you write down and substitute the values. Okay, so we'll get this as 3.19 into 10 raised to minus 19 coulomb. So let me move on to the next problem. A charged oil drop is just floating in a uniform electric field. Electric field is given again, but it is given per centimeter. It is we need to substitute the value per meter here. Okay, while solving the problem we have to write it in terms of meter. Find the charge on it. Charge is to be determined and the mass is given again. The similar type of problem, say here it is converted now. 300 into 10 raised to plus 2, because it is in the denominator. Per centimeter means the centimeter conversion is required in the denominator. So 10 raised to minus 2 we have to write in the denominator. If it comes to the numerator, it will be 10 raised to 2 here. Okay, so E is to be determined. Again, write the same condition. Calculate the charge value. It comes out to be 3.185 into 10 raised to minus 18 coulomb. Okay, so one more problem of the same type. It is an oil drop of diameter 3 into 10 raised to minus 7 meter carries an electric charge. Okay, calculate the electric field necessary to keep it stationary. Electric field is to be determined. The density of the oil is given as 900 kg per meter cube. List out the values. Diameter is given here. We need radius for our calculation. So divide this value by 2 and take a radius value here. Density is given. The strength of the electric field is to be determined. Okay, right? So the answer comes out to be 778.91 volt per meter. Okay, now we will move on to the problem on specific charge of an electron. Okay, a cathode ray beam is bent in a circle of radius 0.02 meter by a field of magnetic induction 4.5 into 10 raised to minus 3 Weber per meter square. Calculate the velocity of the electrons. Given charge of the electron is given and mass of the electron is given. Okay, list out the given values. Radius is given, magnetic field is given, charge is given, mass is given. So now the condition what we have to write here is when the beam is bent in the form of an arc means the force experienced by the magnetic field must be equal to the centripetal force here. Okay, so whenever the particle is taking in a curved path or moving in a curved path, so the two forces will be balancing here in presence of magnetic field, that is BEV must be equal to the centripetal force mv square by r here. So what is required to calculate here? So V is to be determined. So just write down the expression so that we can calculate a E value. Then substitute all the values in this. Okay, substitute the field value, E value, R value and M value. We'll get the final answer as 1.582 into 10 raised to 7 meter per second. Okay. So next problem, an electron accelerated by a potential difference is given at 5 kilovolts, 5 into 10 raised to 3 volts, enter a uniform magnetic field is mentioned here, perpendicular to its direction of motion. Determine the radius of the path of the electron. Again the same condition we have to make use here. Okay, so 5 kilovolt, while solving the problem you write this as 5 into 10 raised to 3. Okay, so same condition we use. Write down the formula and okay. So but one thing is here, what is asked to calculate, determine the radius of the electron. Radius is given here. Radius is to be determined. Okay, m into v, that is not given directly. So first we need to calculate the velocity in terms of the energy. Okay, so velocity is not mentioned directly as in the previous problem. So we have to make use of whenever the electron is moving with a certain velocity, it acquires some kinetic energy. So E is equal to capital E, or kinetic energy is equal to half mv square. So the energy acquired can be written in terms of potential difference as E into V, because the V, capital V potential is given here. Making use of this we can do the calculation. So just do the cross multiplication. We will get V as root of 2 EV by M. Okay, then just make an adjustment. If you want to do the calculation directly, we can do like this also, or if you want to make a simplified manner, everything want to be in under root, you have to push this into in under the root here. Just square it, square it, square it, and take it inside and cancel out the things which will get cancelled. The common things are there. E and E is common and M is common. So by making that type of calculation also you can do. Otherwise you can keep it outside, and if you have a calculator with you, so without doing these adjustments also you can do the calculations. Okay, next problem. A 2 kilovolt electron enters a magnetic field of 5 into 10 raised to minus 4 Weber per meter square. If the radius of the electron path be 0.303 meter, find E by M. Okay, E by M is asked to calculate. It is now write down again similar condition we are going to apply here. Okay, so but E by M, reduce this formula to E by M. Just you keep this in the left hand side itself and take this M and cross multiply it, you will get V by RP. Okay, so again using a similar type of calculation as in previous case, because the potential is given, velocity is not mentioned, so convert the potentials in terms of velocity in terms of potential and substitute it. We'll get the final answer as 1.75 into 10 raised to 11 coulomb per kg. Okay, just substitute all the values here. All the values are given. Okay, into 1 by RB is here. Okay, now we shall move on to the problems on Frankhertz experiment. In Frankhertz experiment, the first dip in the current was observed at 10.2 volts. Okay, calculate the wavelength of light emitted by hydrogen when excited to the first excitation level. In these solving the problems on Frankhertz experiment, the only formula we have is E is equal to h nu. So whatever is required to calculate, in that way you can convert this equation. Okay, if wavelength is asked, we have to convert that because nu is equal to C by lambda. Okay, just keep on convert it, and whenever electric field can be written in terms of energy, energy can be written in terms of E into V, where V is the applied potential. Okay, so list out the things here, that is potential is given as 10.2 volts and wavelength is to be determined. Okay, so substitute the values. So just cross multiply it. Hc by Ev it becomes, okay, h is a Planck's constant, okay, 6.6 into 10 raised to minus 34, and c is the velocity of light, 3 into 10 raised to 8 charge of an electron. So in this problem all these constants are not mentioned. Okay, so you have to remember all the constant values such as Planck's constant, velocity of light, charge of an electron, mass of the electron, Boltzmann constant. Whenever it is required, you can substitute and do the calculation. So after doing a calculation, we'll get the answer around 1.213. So double time this multiplication quantity has appeared here. Just it's a 1.213 into 10 raised to minus 7. Just you cancel this one into meter. Okay, or if you want to express this in angstroms, you can express it as 1213 angstroms, because 1 into 10 raised to minus 10 meter is nothing but 1 angstrom. So express it in terms of angstroms. Okay, another problem. With Frankhertz type of experiment on sodium, the first spectral line to appear is the D line. Sodium lines are usually referred as D lines of wavelength 5890 angstrom. Calculate the first excitation potential for sodium. Okay, the wavelength is given. So V is to be determined. Again same formula, E is equal to h nu. Write this as E into capital V. V is to be determined. Cross multiply and hc by E lambda we will get. Okay, hc by E lambda. Substitute all the values here. H value, C value, E value, and wavelength is given. Okay, so it comes out to be 2.1 volts. Now we shall solve few problems on Stern-Gerlach experiment. A beam of silver atom in the Stern-Gerlach experiment obtained from an oven at 1500 Kelvin. So this is capital T. Okay, a temperature is given. Passes through an inhomogeneous magnetic field of field gradient. Field gradient means dB by dx, 2 Tesla per meter, perpendicular to the beam. The pole pieces are 0.1 meter long. Capital L is given. Calculate the separation between the two components of the beam on a photographic plate. Alpha is to be calculated here at a distance of 0.5 meter. Okay, so length of the field is given as this much. At this distance we need to calculate a separation alpha value. Mass of the silver atom is given here. So list out the given values: temperature, field gradient, length, okay, and mass. Okay, so now the formula, this already we have discussed in our previous sessions. The take away the direct formula of this one, and this is not mentioned directly. Again we have to write down the value. This is nothing but a Bohr magneton. Okay, Bohr magneton is to be substituted there. Okay, so now you just take the value of this one, half kT. In the previous problem I have taken energy as half mv square. The energy also can be taken in terms of thermal energy. It is capital E is equal to K into T, where K is a Boltzmann constant. So that formula I have made use here to calculate the velocity. Okay, so now you see, right, written here, energy, thermal energy is nothing but kT. So in place of energy, half mv square is equal to kT. Substitute the value. V is equal to, V comes out to be this much. So let us use this velocity in the calculation. Okay, right, substitute all the values. All the values are now with us. So this is at the end of the pole pieces, but in the problem it is to be calculated at 0.5 meter. Okay, so write the formula like this: the separation of the lines according to the plate is given by, so what we got here, and distance of the plate from the magnetic field, so divided by length of the pole pieces. Right, so substituting this, we'll get the answer as 1.1175 into 10 raised to minus. I hope I understand on. So simple mathematical calculation it is. Okay. So what we take at point 1, you are getting a deflection, that is deviation, as this much. At 0.5, what it is. That way we are doing the calculations. Okay. Simple mathematics we have made use here. Okay, again one more problem, similar type of problem. In Stern and Gelack experiment, silver atom traverses a distance of 0.1 meter in an homogeneous magnetic field of field gradient 55 Tesla per meter. If the velocity is given directly in this problem, okay, so 450 meter per second. Calculate the separation between the two traces on the collector plate 0.5 meter from the pole pieces. Mass of the silver is given and Bohr magneton is mentioned here. So in the previous problem it was not mentioned. So again we have to remember this value also. Otherwise you can even calculate the Bohr magneton formula is EH by 4 pi m. So instead of remembering this value, because in the calculation, while doing the calculation, we will be remembering the Bohr magneton theory, that is a mathematical formula, that is EH by 4 pi m. If you know that also, we can do this calculation, because all the values will be, constants will be known to us. Okay. So please take a values, and similar problem. It is similar way we have to calculate. First you calculate the alpha value. The formula is half dB by dx, the same formula as in the previous one, half dB by dx into mu by m into L square by V square. Okay, half dB by dx, okay, mu by m into L square by V square. So if we do this calculation, now we have to calculate this deviation at 0.5 meter. Same formula. Okay, so the answer comes out to be 3.489 10 raised to minus 4 meter. Okay. Now we shall move on to the last chapter problems, that is vector atom model itself. Here you see the calculate the value of Bohr magneton. Just now I explained that the Bohr magneton formula, we are always familiar with this one because many times we have used in our derivations. Okay, in this module. Okay, so H cross by 2m also you can write, because H cross is nothing but H by 2 pi, EH by 4 pi you can write. Okay, and in this type of problem they have not mentioned not even a single constant value. You have to write everything by yourself. If the problem is like this, calculate the value of Bohr magneton. See, in this it is that they have not at all mentioned any of the constant values here. So all the values are known to us of electron. This is a Planck's constant. Keep on substitute the values here. Okay, so this is E value, H value, okay, 4 pi value, and mass of the electron. We will get this as 9.272 into 10 raised to minus 24. Okay, So next problem. The experimental value of Bohr magneton is this. Calculate the specific charge of an electron. Okay. So write down the Bohr magneton formula. Just you retain this E by M in the left hand side so that you can calculate a E by M. Specific charge is nothing but a E by M. Okay. So all Bohr magneton is given. H will be known to us. You can do the calculation. Okay. So it comes out to be 1.75 10 raised to 11 coulomb per kg. Now the last problem of this session, calculate the number of electrons occupied in p subshell and also calculate the total number of electrons in m shell. Okay, so the number of electrons, maximum number of electrons occupied in a subshell is given by the formula 2 into 2l plus 1. Okay, so L value is P. For P, we have to decide a L value because L can take the values from 0, 1, 2, 3 to n minus 1 values. 0 corresponds to S, 1 corresponds to P, 2 corresponds to D. In that fashion, we have to select the value of L for a given suborbital. Okay, so as it is P, you can write L is this one. The formula for calculating is maximum number of electrons that can be accommodated in each subshell is given by the formula 2 into 2l plus 1. Substitute the value of L here, you will get the value of number of electrons in P is, and this is already known to you, but only thing according in a systematic manner with the formula I have to show that it is 6 electrons. Now they are asking you to calculate the number of electrons in the M main shell. That is the formula we have to take 2n square. So for M means K is the first orbit, L and M. So N is equal to 3 you have to substitute for calculating this one. So it comes out to be again 18 electrons. Okay. So with this we have come to an end of the numerical.